Our second keynote speech is on machine learning for machine learning compilers at Google, given by Dr. Phitchaya Phothilimthana, or Dr. Mangpo, who was born and raised in Phitsanulok. She was the first female student to represent Thailand at the International Olympiad in Informatics, where she received bronze and silver medals in 2006 and 2007 respectively.
She received an undergraduate degree in computer science from MIT and PhD from UC Berkeley. Dr. Phothilimthana was a recipient of the Microsoft Research PhD Fellowship and Qualcomm Innovation Fellowship. She is currently a research scientist at Google DeepMind, where she leads the Machine Learning for Machine Learning Compilers effort, which is one of Google Brain moonshots in 2020.
Her research interests include compilers, machine learning for systems, and computing sustainability. Ladies and gentlemen, Dr. Phothilimthana.
Good morning, everyone, and thank you for inviting me to give the keynote speaker as a keynote speaker today. I'm really honored to be here, especially at this biggest CS conference in Thailand, and this year here in Phitsanulok, where I grew up, and it's my hometown. So I'm very excited to be here, and also very excited to share about the current research that I'm working on at Google. So I joined Google about almost 5 years ago, and since then I've been working on and leading the research effort in machine learning for machine learning compilers. And I probably don't have to motivate you why machine learning and AI is really important, but you may not know that in order to enable this machine learning and AI to run on all sorts of applications, you need to run them very efficiently. And one of the key components to make them machine learning run efficiently is a compiler, which is the topic that I'm working on. So if we're looking at the system stack for production machine learning workloads at Google, you will see that at the top we have high-level frameworks that let the application researcher or engineer to write various sort of machine learning models. So these frameworks include things like TensorFlow, PyTorch, and JAX. And in the middle, we have XLA, which is a compiler, which is a tool that essentially translates programs written by the user and then translate that into something, into binary or executable that hardware backends that can run. For example, these backends include CPU, GPU, and TPU, which stand for Tensor Processing Unit. In this particular project, we are focusing on optimizing the XLA compiler to run very efficiently on TPU, because at Google, TPU is the most heavily used accelerator for machine learning workloads. So the goal of the project that I'm working on is to enable automatically setting the best configuration of the compiler for all sorts of machine learning workloads that run in Google Data Center. How do we do this? So let's take a look and understand what exactly is the compiler first. So a compiler is a tool that essentially transforms program written in high-level language by human and translate that into low-level representation that understand by machines. And through this translation, the compiler have to optimize all sorts of problems. And these are usually very complex optimization problems. So to do that, we usually build heuristics to solve these complex problems. Now, these heuristics may solve these problems really quickly. It's usually in linear or polynomial time. But that comes with some disadvantages that sometimes the solution found by the heuristic might not be optimal. So we built an autotuner, which is a tool that aids the compiler to find better optimization decisions. And the autotuner does this by, instead of relying on a heuristic, it defines it as a search problem and try to find it searched the space of all possible configurations and try to find the one that gives the best performance, for example, in terms of program runtime. So here's the overview of the production XLA compiler that we use at Google. The input to the compiler is a program, which is represented as tensor computation graph. The tensor computation graph have nodes that represent tensor operation. You can think of these as a high-level operator like matrix multiplication, convolution, element-wise addition. And the edges represent the data that flow between these operators. You can think of these data as matrix or tensor. In the compiler, there are two classes of optimizations. The first class of optimization is graph-level optimizations. These optimizations require knowing about the entire program graph in order to make good decisions. So these optimizations include things like layout assignment, meaning that we have to assign the physical layout for all of the tensor that occur in the program. Or memory assignment, picking which types of memory in the device that we should save the tensor in. Typically, after these graph-level optimization, we are going to get a set of kernels where each kernel represents as a fused subgraph. At this level, we can do further optimization independently within each kernel to generate low-level code. So optimizations at this level include things like tiling, loop tiling, in order to bring in the tensor that live in the slow memory into fast memory. So we built Autotuner for the XLA compiler for various optimizations that highlight in colors. In particular, the ones in orange are the optimizations that we have built the Autotuner for, and the Autotuners are actually used in production. And the one in blue are the one that we have the Autotuner built and ready, and we try to deploy that in the production very soon. And the green ones are the more experimental Autotuners. So as I mentioned earlier, what Autotuner does is that it essentially searches in the space and try to find the best configuration according to some sort of performance metric. This could be runtime. So through this process, when we try to evaluate if that configuration is good or not, we rely on an evaluator. So usually, to do this, we will have to compile and run the program on the real hardware, which can take quite some time. And in this picture, I highlight the yellow components here, and this is where machine learning comes in. We also try to apply machine learning to help speeding up the search process, because the Autotuner may take a long time to search in the space, and we apply machine learning to help the Autotuner discover the best configuration. But before we go into that component, let me first explain how we formulate optimizations as search problems for the Autotuners. And in particular, for this talk, I'm going to give example on how we define the search space for layout, operator fusion, tiling, and flex tuning problems. So first of all, we defined a path configuration for a particular tensor computation graph on a particular optimization path as a collection of per node configuration, where the node refer to the node in the computation graph that you see earlier. And these configurations essentially control how the path transform the graph in the compiler. So let's take a look at a concrete example. So here is a layout assignment problems, where on the left side you see an example tensor computation graph with 4 tensor operation nodes. So at each node, the edges represent tensor. So when we have a tensor, we have to decide how the tensor would actually be stored in memory and how it's actually physical being laid out. So at the edges here, we highlight the tensor by its physical layouts. So for each node, we have the layout for its input and output. So this is how we control the compiler to assign the layout. Now, you may see in this example that the edge between add and convolution have a conflicting layout. What does this mean is that when this happens, the compiler have to transform the layout by inserting a copy or a transpose operator to fix the layout mismatch. So in this layout assignment problem, we essentially have to solve this complex optimization problem by selecting the right layout in a way that we should make each of the operation run as efficient as possible, but also minimize the number of copy or transport operator, which add the overhead of the format conversion. So it is a pretty complex optimization problems. So to define the search space for this, one easy way is that we can consider all the tensor, all the input and output of each node independently, and consider the permutation of its dimensions. And then it turns out that when we do this naive search problem definition, there turns out to be a lot of invalid configurations in the search space. So it makes it extremely inefficient to search in this search space. So instead what we do is that we look at a more compact definition of the search space where we only consider the layout options for the important operations, which include convolution and reshape. And then for each of these important op, we get the valid combination of input and output layouts from the XLA compiler itself, and then leverage the layout propagation algorithm of the compiler to propagate the layout from that important operations to other nodes in the graph. So with this formulation, the search space is much more compact and only include valid configurations. So it makes the search much easier to find a good configuration. So next, let me give you another example of operator fusions. So in this problem, we want to fuse some of these tensor operators together. Why do we want to do that? So when we fuse things together, for example, in this example, we fuse add and reshape, add and copy together. What it means when we fuse these nodes together, it means that the intermediate output between add and reshape doesn't have to be safe in the main memory, right? It essentially can be consumed by reshape immediately. So it reduced the traffic to the memory and also reduced the amount of memory that we need to store these intermediate tensors. Now, operator fusion is not always good. Even though it's reduced this memory traffic, it can also incur some overhead. So in this example, we used to have one add, but since add have two consumer, reshape and copy, when we fuse add to those two consumers, we end up having to recompute add twice. So that's add up to the overhead. So in this optimization problem, we have to balance between whether we want to reduce memory traffic or incurring the recomputation. So in this particular problem, the way we frame this as a search problem is to define a fusion configuration bit for each node in the graph. So in here, you can see that each node is level with either 0 or 1. So 1 means that we do not want to fuse that node to its consumer. 1 means that we would like to fuse that node to its consumer. So in this case, we say that add should be fused to reshape and copy. Another important optimization that is worthwhile for auto-tuning is tile size selection. So tile size selection is a problem where, for example, let's say you want to compute matrix multiplication on GPU, right? So what happens is that you can store the entire matrix on the HBM memory, which is the large, but it's relatively slow memory. Now, these accelerators usually have a smaller but faster memory, which usually cause scratch pad. So what you can do is that instead of compute the entire matrix at once, you can bring in some smaller tiles of the matrix into the faster memory, into the scratch pad, and do the computation for each tile at a time. So this significantly speed up these computation kernels. Now, when we decompose the problem into tile, we have to pick what is the best tile size. So this problem is essentially pick the optimal tile size for that particular kernel. In this problem, since the valid configuration of tile size are actually not that many, so we can enumerate all possible choices, try them all, and try to find the optimal ones. So let's take a look at some of the results. So here we run our layout, fusion, tile size, auto-tuning on about 150 machine learning models, both inference and training. And these models are representative of models that use in research and production at Google. And In summary, we found about 5% average speedup across all of these models. And in this chart, we show the speedup per each model, and we highlight the one that gained more than 5% speedup. So overall, on some of the model, we can gain a large amount of speedup. For example, on one of them, we gain speedup as large as 2.4 times. And about 13% of the workloads, we achieve about 10% or more speedup. In this chart, I also break down the speedup by types of auto-tuning. And you can see that layout and fusion tuning offer the most speedup, whereas tile size auto-tuning offer moderate speedup, but across all of the models. So now that you know how we define the search space, and you can see that sometimes the search space can be extremely large, right? So the process of tuning these workloads can take some time. So in the previous experiment that I show you, for each of the optimization, we run the auto-tuner for 1 hour. So if we have 4 optimization, that means it takes 4 hours to run the auto-tuner, and it's also running on multiple machines, not just one machine. So it requires some time and resources to run the auto-tuner to find these optimal solution. So how can we accelerate this process and reduce the amount of resources used? This is where machine learning comes in. And one of the things we try is to try to reduce the evaluation time. So in order to evaluate one candidate, whether it's good or not, what we usually do is to compile and run the candidate on the hardware and measure the runtime. But that actually takes quite significant time. So instead of doing that, we built a learn cost model to predict the runtime for that candidate. So let's take a look how we do that in detail. So essentially, we can think of this problem as we have a graph that represents the computation graph that we would like. Now, the graph for the entire program can be huge, but that can be decomposed into multiple subgraphs that we call kernels, because that's an independent executable unit. So once we have a smaller subgraph, or kernel, we can then try to predict the runtime for the kernel. If we can predict the runtime for the kernel, we can then sum them up to estimate the runtime of the entire program. So we decompose the problem down to, let's try to use machine learning to predict the runtime for each of these kernel that represent as a small subgraph. So since a kernel can be represented as graph, the best model that we think that can solve this problem efficiently is a graph neural network. So what we do is that we essentially feed information to graph neural network, including things like opcodes ID, meaning that the information about the types of the node, like convolution or matrix multiplication. Right? So that is encoded as opcode ID, which then get translated into opcode embeddings by using a learn lookup table. And then we feed in additional information that is important, such as tensor size, rank, padding, striding information for that particular node as the extra node features. And then we also have to encode the configuration information, for example, the tile size. To do that, we essentially repeat the kernel configuration and concat that with the node features and feed that as the node information to the graph neural network. Graph neural network also takes in the structure of the graph as input and then output the final node embeddings. Now that we have node embeddings, we can then reduce the node embeddings to represent the entire graph embedding or kernel embedding. Now, there are multiple choices that we can try to do here. We can try to do a simple reduction by sum up all of them or do an average pool. We can also do something more complex, like using an LSTM or transformer model to get the kernel embeddings. Once we have the kernel embedding, we can then use that, feed that through the feed-forward layer to get the final runtime prediction. So let's look a little closer to the graph neural network that we are using. In particular, we use GraphSage, which is one type of our graph neural network. And what it does, essentially, it's try to basically aggregate the information from its near neighbors to generate the node embedding. So in one iteration of GraphSage, what it does is that it gets the embedding of the node that it's one hop away from that particular node, concatenate with the current embedding, and feed that through a linear layer to get the updated embedding for the node. So if you actually run multiple iterations of the GraphSage, or you can think of running multiple layers of GraphSage, you end up basically aggregating information of neighbors in multiple hops. So for example, if your GraphSage have 2 layers, you would end up something that look like in the picture, where you aggregate the information from neighbors that are 2 hops away. And once we have the model architecture, we also need to decide what kind of loss function that we use to train the model. And we consider 2 types of loss functions. The first one is a typical one that people use in a regression task, which is mean square error. So it's essentially compare point-wise the error between the target and the prediction and square them. Alternatively, because in our problem, sometimes we don't actually care about the absolute error, but we care more about the ranking of different configuration, right? Which configuration is faster than others. So we care more about these ranking or relative runtime. So because of that, we can consider pairwise rank loss. And what this loss function does is that it's sort of counting the number of pairs that the model gets correct or incorrect. And to evaluate the model, we consider 2 tasks. The first task is tile size selection. Given a particular kernel, enumerate all possible tile size options. We want to select the tile that have the fastest runtime. So in this particular task, we care more about a relative runtime of the configurations. Where the second task is fusion, where we have an arbitrary fused kernel. We would like to predict at the absolute runtime of that fused kernel. And this is useful because when we can predict the runtime of a fused kernel, we can then consolidate them and estimate the runtime of the entire graph. And we compare our model with a baseline, which is an analytical cost model written by human developer, which takes very long time to develop. This particular model is actually used in the production compiler to do tile size selection, so it's built specifically for the tile size task. We adapt the model to also make it work with the fusion task as well. And here's the result. This table shows the error predicted by the learned model and the analytical cost model in terms of percentage. So lower is better. And you can see that on the test graph, our learned model error is really low. On average, it's about 3 to 4%. And if you can compare to analytical cost model, it's smaller on pretty much all the models except one. If we look at the fusion task, our learned model have a similar error overall, but if you compare to analytical cost, much smaller. And this is because the analytical cost model is not built specifically for this task. That's why the error of the analytical cost model is smaller. And this also highlights another advantage of using learned model, because what we need to do is that we just need to build the model once, just retrain the model on a different set of data. Whereas if we have to build the analytical cost model, we have to spend a lot of time tuning the analytical cost model for that particular task in order to get a really accurate solution. So a few key takeaways that we get from experimenting with this learned cost model is that if we are interested in the ranking or relative runtime of different candidates instead of the absolute runtime, it is much better to train the model with rank loss. We found that when we use rank loss, the model can learn much better than using a typical regression loss like mean square error. And the other thing we learn is that once we already used a graph neural network to get the node embeddings, we can simply do a simple reduction to get the graph level embedding. And the performance of doing this simple reduction is very comparable to doing something more complex like using LSTM or transformer. So since we get a pretty promising result using the learned cost model, what we do is that we try to integrate the learned cost model with the autotuner. And the way we use it is to use the learned cost model to essentially get the predicted runtime of all the configuration, and then select the top K best configuration according to the learned model and run that on the real hardware to pick the real one, to pick the really good one. Because we know that, okay, the cost model is not always perfect. There are some errors. That's why we have to, verify that some of the candidates on the real hardware. But notice that the number K is usually much, much smaller than the number of the search space. So we actually deployed the learned model for the tile size auto-tuning in production using this strategy with the learned model. And we found that by using the learned cost model, we reduced the search time of the auto-tuner by 20x, which means that we enable tuning 20 times more kernels per day. And one of the things that we actually do in production is that we have to make sure that our model is up to date. So for example, if we train our model a year ago, right? And if we try to use that model again today at the current workloads, because machine learning workloads change over time, it's evolve over time, there are new types of machine learning models that comes up, meaning that the model that we trained a year ago is probably not going to work well at the current workloads we have today. So instead, what we do is that we periodically fine-tune the model using the live production data. We actually do this every day, but instead of retrain the whole thing from scratch, what we end up doing is that we freeze the pre-trained graph embedding layers. So the one in the box, we freeze all the weights, and then we only fine-tune just the prediction heads with the latest data. So we found that this strategy works really well in practice. Next, since this worked really well at the kernel graph, subgraph level, we think that, hey, can we actually scale this to work at the graph level to predict the runtime of the entire program? Unfortunately, this problem is much, much more difficult because the scale of the graph is extremely large. So if we look at the kernel graph that we predict in the previous experiments, usually the graph is about fewer than 100 nodes. But if you look at the graph of the entire program, it could be at 10,000 nodes. Actually, the biggest graph that we have seen in our data center is as large as 500,000 nodes, which is huge, right? So how can we scale our approach to work with this extremely large graph? What we do is that, how about we partition the graph into multiple segments, right? Where each segment is somewhat small and manageable. So once we have smaller segment, we feed each segment into the model, the same model that we have, to get the runtime for that particular segment. Now we have multiple runtime for multiple segments. We can sum them up to get the final prediction runtime. So that seems like a good idea. So we do that, but turns out that if we actually keep the gradient of all segments around, we still run into the issue because usually a device will not be able to save all the activation that required to do the backward propagation. So instead of doing that, we say, then let's do the gradient descent update on one of the segments, right? And discard the activation for the rest of the segments. So that's what we do. So in this figure, I basically just highlight that in one iteration, we randomly select which segment we're going to run the gradient descent on, and we only keep the activation for that particular segment. So this actually works, and we can train arbitrary large graph using this strategy without much accuracy loss. The other idea that we try is similar to dropout. So in machine learning, dropout is a very common technique that people use to get better generalization. But usually, dropout is at a very fine granularity. Instead, in this work, we try to apply this dropout idea, but at the segment level. So in each iteration, we also randomly select some subset of the segment to be dropout. So the advantage is that when we do this, we can accelerate the training time by a lot. But when we drop things out, we also need to make sure that we compensate for that. So we do that by upweighting the active segments. So here is the quick results. Here we show the validation score when we use these techniques, and here higher is better. So if we look at the training curve over time, the blue line shows the segmented method that, okay, this is the best method. But when we look at the validation score, which is the bottom graph, you can see that the green line is actually better than the blue line, where the green line is the segment method combined with the dropout approach. So what it suggests is that these techniques of dropping out some of the layer actually help the model learn to generalize better to unseen problems. So that is some of the ongoing research that I'm working on. And I'm just checking the time that I think I still have a few more time. So let me go into another component that we also try to use machine learning. So instead of using machine learning to just predict the runtime, we can also use machine learning to help guide the search directly to the promising search space. So in this part, we explore various different kinds of search strategy. We look at a common search strategy, very simple, non-machine learning. This includes search, like exhaustive search, simulated annealing, evolutionary search. But we also look at a more advanced search that use machine learning, for example, model-based optimization and deep reinforcement learning. So I'm not going to go into the detail of the first three because they are very basic and very common, but I'll briefly go over the machine learning-based model. So the first one we consider, we call it model-based optimization. This technique essentially considers a set of candidate regression models, including things like rich regression, random forest, gradient boosting. And with this ensemble of models, what we do is that we select good model to find an acquisition function. And we use this acquisition function for the evolutionary agent to propose the next batch of candidates. Now, for this particular optimization, we don't really encode the problem context. So the model always learns from scratch at the very beginning of each search run. Where the next strategy that we consider, which is deep reinforcement learning, for this one, we also encode the problem context, which is the graph being optimized for the model to learn. So to encode the problem context, which is the computation graph, we also use graph neural network to encode the problem, very similar to the learn cost model that we have. So we use graph neural network to produce node embeddings, and in this particular problem, we use segmented recurrent attention layers, which is transformer XL, to then combine the node embeddings to graph embedding in order to capture long-range dependency. And one thing that our approach is slightly different from a typical RL approach is that in a conventional RL approach, they usually use autoregressive techniques where it usually make a series of decisions. So in our problem, you can think of it decide the fusion configuration for one node and then move on to the next node and the next node over time. So that would be an autoregressive style. However, in our problem, because the one graph can be extremely big, if we use an autoregressive scheme, it may take a long time to train the model. So instead, we consider use a non-regressive RL, where we actually predict the configuration for all the nodes at the same time. And it turns out that this actually enabled the model to learn much faster. And here is the result, where we showed the speed up found by the autotuner when the autotuner used different types of search techniques. So higher is better. And now, to our surprise, we found that the non-machine learning based search techniques actually perform consistently better than the ML-based search techniques. And we hypothesized that this is because the search space is very high dimensional, so it's pretty hard to learn an accurate model to fit that data without prior knowledge. Now, it's possible that perhaps some sort of pre-training could help the ML-based model to learn better, but we have not run an extensive study on that types of experiments. Now, I would like to spend the last part of my talk touching on a bit about how we actually use this technology in production at scale at Google. So we have shown that, hey, like using Autotuner, we can actually speed up a bunch of various different models, but how can we get this to use in production? So my collaborator had this brilliant idea about, at Google, we have this infrastructure that we can profile all the things that actually run in our data center. So that's what we do. Every day we profile what types of workloads that are running on TPUs by how many hours on how many chips. So with that information, we can get the top workloads that run at Google every day. Since we have that list, we feed that into the autotuner. So the autotuner will auto-tune these workloads offline every day. Once we have the auto-tuning result, we summarize them and extract them. We call that an FDO profile. And we save that profile, which is the best configuration, we check that into the compiler as an embedded database. So the next time when the autotuner, or when the compiler compile and run the program again, it will look up the database to see if there's a configuration for that workload or not. If there is, it will look up the database, use that configuration to compile. If not, it will fall back to use the default heuristics. So with this strategy, we have been deployed the tile size auto-tuning and some flex auto-tuning to optimize the top workloads that run in our TPU fleet every day. And we have been saving about 2% of the total TPU consumption time. And if you look at the saving versus tuning cost ratio, it's about 15%, meaning that we use about one TPU to save about 15 TPU worth of time. And as I mentioned earlier, we actually use the learned cost model with our autotuner, which enable us to tune 20 times more kernels per day. And additionally, apart from using our autotuner to tune these fleet-wide workloads, we also use an autotuner to target really important serving model that serve in Google production. For example, we use the autotuner to tune and find Speedup on the ranking model that used in Google search. So we basically deliver about 18% Speedup on the search ranking model. And more recently, we also use Autotuner to help speed up the most recent state-of-art model that serve in production. And with that, I'm gonna leave you guys with this slides, which lists a bunch of publication related to the work that I'm talking about today. So if you're interested, you can check this out. And with that, I would like to thank you for listening, and I'm happy to take questions.
Thank you very much, Dr. Mangpo. Now it's time for Q&A. We have only two questions. Please. Microphone, please. Microphone for our guest. Hold on. We have a microphone coming. Over there. Could you please, your name and
sure. Hi, my name is Phitchaya from NECTEC. Thank you for your impressive presentation and also brightening our morning. So I've got several questions, but if we have time, okay. So in the in your presentation, you have mentioned the XLA, which is basically a compiler for complex computation network. So in a large-scale computation like pathway architectures, I think it belongs to Google as well, there will be a case of hardware failure. So how can you actually handle that problem regarding the reinforcement learning?
Okay, so essentially, yes, there are hardware failure problem when you train these machine learning workloads at extremely large scale. So you mentioned Pathway, which is another system that actually builds on top of XLA to handle this like training extremely large model. So when you run machine learning model at that scale, you born to encounter some of the various types of failure, and one is hardware failure. Yeah. Yes, and so that is like a different problem than compiler problem.
Oh, right.
Yeah, so it's more like a runtime problem where you already succeed at compiling the program, you already have the binary, you have to run that on the hardware, but on the real execution, from time to time the hardware may fail. So it's more like a runtime problem, and that's we have a different solution on how to do that. Yeah.
Ah, I see. That helps a lot.
Yeah, so I think like for the problem we are focusing on, it's about like how we compile the program to generate something that runs faster. But once you already solve that problem, there are other problems like how to deal with these failure, which is at a different level of the system stack.
Okay, and regarding your results, I think it should be better if you can also compare by labor quantification regarding the human efforts in optimizing the model, stuff like that. Is it okay to do that in Google's view?
So yeah, there are different metrics to report how important these improvements are, right? So in my slides, I report the speed up compared to the baseline, which is, if you run the normal compiler, this is how fast the program will run and how much speed up the autotuner deliver. So I just report that in terms of percentage. Internally, when we, say how important our project is, we can actually translate that into like dollars amounts.
All right.
Which is kind of like, you can also then like convert the dollars amount to like, how does that transfer to like 1 SWE hours, right?
Right.
So we do have that internal conversion, but I'm not allowed to really say the absolute number here.
Okay,
yeah.
That's okay.
Right.
Okay, in the last question, this is going to be my last one.
Okay.
In a broader view, what would be the bottleneck for speeding up the training process in a large-scale model just like this?
I think there are multiple things. So I will just list a few. I don't think it's exhaustive,
sure, yeah.
right? So one is definitely communication costs. Once you talk about the extremely large scale model, they don't run on one machine anymore. They run on a large number of devices, and they have to communicate to, like some of the gradient and everything. So that can take quite an amount of time. So a lot of research is going into, okay, what is the best way to do model parallelism? What is the best way to partition the model or sharding the model in order to reduce this communication time? So I think that's one of the big thing. There's a lot of research and efforts into optimizing that, but I think there are more to be done. So that's one thing. Another thing would be with the scale of models that we have today, they are growing larger and larger over time, right? And we are kind of like at the limit, but people still want to keep scaling them. So if we want to train the next largest model, largest than GPT-4, for example, like how do you enable that? Okay, maybe you can throw more GPUs to it, but at some point it's not gonna scale anymore. So we would have to look into techniques on how to reduce the resource consumption. So now I think the really hot topic that I think a lot of people should pay attention is to doing quantization or sparsity, which I think it's the area that we haven't leveraged that enough. Yeah.
Okay, thank you very much.
Thank you for your questions. Next question, please. Just one more question. Anyone? Yes, please. The gentleman over there.
สวัสดีครับ ผมชื่อ Phitchaya นะครับ จาก Phitsanulok นะครับ ผมอยากจะถามว่า ใน Untitled Chapter นะครับ มี Chapter ที่
Yes, go ahead. Yes.
Okay, my name is Perrin, and I'm a high school student, and I'm just looking at this. And I was really wondering regarding the section about the LSTM and transformer performance when you said that if you did not use transformers or recurrent neural networks, you would have a comparable performance to just without using it. So could you please, just for a little more clarification, could you please state how, how do you model it into like a recurrent form? How do you model these graphs embeddings into a more recurrent form, please?
Yeah, so for that specific problem, right, the problem is that we have embeddings for all the nodes in the graph, but in the end, we actually want to get the final prediction of the entire graph. So you have to basically reduce all the nodes into one embedding, right? So we call that graph embedding. So like, what is the best way to reduce node embeddings to graph embedding, right? So when we use a sequence model like LSTM or transformer, we essentially just consider topological order of the nodes in the graph and feed that into LSTM and transformer in that order. So that's how we frame that as like a sequence. Now, the fact that it doesn't help much, and this is I believe it is, I hypothesize that this is because the fact that we already have graph neural network that already encode the graph structure in the graph, and that's why we don't need another sequence model in our architecture.
Yeah, because I was really wondering, because self-attention is a very powerful mechanism, and so if it doesn't help, then could you share some of the architecture for the graph neural network itself? Like, does it utilize self-attention inside as well?
So there are multiple types of graph neural network. So the one that we end up using is GraphSage that I shown in the slide. It's very simple. Basically, it's just looking at, the connection of the neighbors, right? So what it does is that it essentially captures the more like a local dependency of the nodes, and it turns out that it's already like really helpful. There are also graph attention network, or GAT. We also experiment with a graph attention network as well, so that one have some sort of attention layers in there. However, in our experiment, we did not see that graph attention network is better than GraphSage. But I don't think that the model we have, it's like the best model that can ever be done. I think that there are definitely more improvement that can be built on top of that.
Okay, thank you.
Thank you very much for your question, and also thank you very much, Dr. Mangpo. Okay, now it's going to be a special session, a wise talk. And for those